Hello, everyone, and welcome to this workshop today. I'm really glad to have you all here. This is the fourth in our series of webinars, and I'm just going to give a brief introduction to myself and Quasi while folks get logged on here. My name is Julia Masterman. My pronouns are she, her, and I am the Education and Outreach Specialist for Quasi. Quasi is a consortium of universities for the advancement of hydrologic science. We're a nonprofit organization funded in part by the National Science Foundation, and our mission is to empower the water community in advanced science, the collaboration, infrastructure, and education. We seek to fulfill this mission through our data services, as well as our education and outreach services, among other things. Quasi's data and compute services provide tools and support for the entire data lifecycle, including 2 data repositories. Our hope is that providing this supporting infrastructure, we can help researchers formulate and execute their data management plans, be effective data stewards, and meet the requirements of funding agencies. We also have various community services. These include grants workshops, a summer institute with the National Water Center, webinar series and events, a virtual university, and much more. But this is the fourth in a series of 5 workshops with a morning and an afternoon session. We hope you'll consider joining the last workshop in this series, which will just be the afternoon session next week. But thank you for joining us today, and we hope that you'll join us for the synthesis discussion this afternoon about the interior agricultural region. So today's workshop will focus on the interior agricultural region. A huge thank you to the conveners for putting together this series of workshops, and to CIROH for supporting this project. And thank you to our speakers who took the time to put together these talks for us today. I'll be handing the mic over to Martin in just a moment to describe this project and introduce some of our speakers. But thank you for taking the time to contribute your expertise to the synthesis activity. This afternoon, we'll have a more in-depth discussion and meeting. You'll need to register for it separately if you've not already, but that you can do so at any point during today. I will put the link to access that meeting link for the afternoon session in the chat in just a moment. As we get started, this webinar is being recorded and will be posted on the Quasi YouTube channel. We ask that you use the Q&A functionality to submit questions to our speakers. Feel free to add questions at any time and upvote any that are especially of interest. We'll have time for questions after each speaker, and then we'll have time for much more in-depth discussion later this afternoon. Finally, we expect that all involved with Quasi events uphold the Quasi Code of Conduct and promote and maintain a professional, considerate, and respectful virtual environment. And with that, I will pass it on to Martin.
Yeah, thanks a lot, Julia. Can I share my screen?
Yes.
Yep, here we are. Okay, very good. So this, as Julia said, this is the fourth in a series of workshops. We're focused on the agricultural region. I appreciate people who have been participating in the previous workshops. The last 3, I think we all learned a lot, and some of the key elements of the synthesis are already beginning to become evident. And what I want to do in this presentation is give a brief introduction to the project and how the project fits within the Cooperative Institute for Research to Operations in Hydrology, CIROH, and the NOAA Office of Water Prediction. So the need that we have is to develop models that synthesize our understanding of interactions between the natural and anthropogenic world. We need these models to quantify sustainable water supplies, to predict water-related hazards, and to understand the role of water in the Earth system. And developing these prediction systems can exceed the capability of entire modeling groups, entire agencies, and in many cases, entire nations. So it requires a community of us to come together to try to address these challenging modeling problems. This work is the Cooperative Institute for Research to Operations in Hydrology, or CIROH, is supported by NOAA. Office of Water Protection, and part of the mandate for CIROH is to help improve the national water model. The National Water Model has had several versions, and it's a model that provides continental domain predictions of hydrological processes. The initial versions of the National Water Model land model was applied on a 1 kilometre grid, terrain routing applied on a 250-metre grid, routing on the NHD Plus River Network and a Liverpool Reservoir model. The prediction ecosystem parameter estimation at gauged locations with limited regionalization and fairly simplistic data assimilation methods that are based on direct insertion. The key value proposition here is that the model extends the predictions that are provided by the river forecast centres around the country and provides information for about 2.7 million river reaches across the contiguous United States and adjoining areas. The hyper-resolution paradigm that was adopted in initial versions of the National Water Model has been criticised, in part because there's not sufficient information and computing resources to infer the large number of model parameters, and in part because the hyper-resolution models aren't sufficiently agile to simulate observed processes in specific regions. So the NOAA Office of Water Protection has been developing the next-gen hydrological prediction paradigm, led by Chief Scientist Fred Ogden. The motivation and approach here is that the siloed approach to hydrological modelling does not adequately consider the diversity of modelling approaches at various levels of spatial and process complexity, and it's difficult to identify a single model that's best everywhere, best at everything, and best all the time. So the approach that's being pushed forward by NOAA is to construct a deterministic multi-model mosaic that can represent the diversity of hydrological processes across the North American continent. The challenges that we have in doing that is that land hydrology is immensely diverse across the continent. And if the next-gen system is to realistically predict local hydrological states and fluxes, we need to know what processes matter, where they matter, when they matter, and how they occur. So basically, if we're to construct a deterministic multi-model mosaic across the North American continent, we need to know what the dominant processes are. And in order to do that, we need to provide the synthesis that we're pushing forward in this project. CIROH, the Cooperative Institute for Research Cooperations in Hydrology, is a new cooperative institute supported by NOAA that's geographically distributed across North America, includes partners and members through a number of institutions in the contiguous United States and a little bit in Canada. And it's a partnership between academia, government, and the private sector, bringing together elements of computer science, data science, and domain science to advance science for society. So our goal here is to define the dominant hydrological processes for a continental mosaic of distinct landscapes. And we're iterating in these regional workshops on two main tasks. The first is to identify what the hydrological landscapes actually are. And the second is to develop perceptual and conceptual models for each unique landscape in the hydrological mosaic. And the idea, as I mentioned earlier, is that this process synthesis provides the theoretical support that's necessary for next-gen developers to simulate the salient processes and features of each hydrological landscape across the North American continent. I'd like to give a shout out to our awesome team who are together here. Hilary McMillan is key member of the team. Hilary, as many people know, has been developing a perceptual model database globally, and a lot of her work has been to understand the spatial variability of hydrological processes across large geographical domains. Young Fan is a is an expert in hydrological synthesis. She's led many really important hydrological synthesis papers across North America across the past few decades. Katie van Werkhoven is a partner from the private sector from RTI International, and Katie's been working extensively with operational hydrological prediction over the past couple of decades, and provides a key link between the theoretical work that we're advancing in this project and the operational hydrological prediction. Wouter Knuben is the key scientist on this project. He's a senior research associate at the University of Calgary, and Wouter has been doing a lot of the intellectual work to define the hydrological landscapes and to pull together different perceptual models for each landscape. And then we appreciate our collaboration with Quasi, including Jordan Reed, a key orchestrator of many of activities, the executive director of Quasi, Julia Masterman, who's been orchestrating this webinar series, and Irene Garusi Najad, who's been providing a lot of intellectual input as to how we understand the spatial variability of hydrological processes across North America. So our goal here, to recap, we're in the 4th out of the 5 workshops. We're in the interior agricultural region, and we want to improve the theoretical underpinnings of hydrological models through process synthesis. And the goals of this workshop is to refine initial perceptual models that we have in the interior agricultural region. In my last slide, I wanted to say, of course, this is difficult. A lot of the field research has been focused on individual catchments, making it difficult to generalize results to large domains. And the concerns are, is it even possible to generalize hydrological behavior given the unique character of individual basins? Do we lack the necessary information that's required to develop powerful and exceptionless explanations? And are the problems of underdetermination so pronounced that it's difficult to reduce the ambiguity that we have in different process representations? So what we're trying to do here is to rise to this challenge and systematically formulate, organize, formalize, encode, and evaluate hydrological theories, recognizing that the community's made tremendous advances in our capability to explain and predict individual processes, process interactions, patterns, and scaling behavior. But these process explanations or theories are scattered across research groups, not widely incorporated in hydrological models. And the purpose of the workshops here are to try to bring this information together so that we can improve the theoretical underpinnings of the models that we're developing. So I'll stop there and then pass the baton back to you, Julie.
Thank you. So I think we can dive into our presentations today. Ying, would you like to introduce our first speaker?
Yes, and first, when we say the interior agricultural region, this is a huge swath of the land of the continent, basically from the Appalachians to the Front Range, and also including some of the western river basins and large sedimentary basins like California Central Valley. These are our nation's food production. Our food baskets, our fruit, and our grain baskets, and agriculture is a huge use of water. And agriculture also doesn't thrive in waterlogged conditions. So we have this wide range of hydrologic conditions from east to west, from some places too much water, like the Midwest, upper Midwest, where water table is too shallow, and then to the western part of the continent where it's too little. So agriculture requires groundwater pumping for irrigation. These are some of the outstanding features compared to the more pristine environments we have been talking about so far. So our talk today will go from east to west, sweeping across this huge landscape. And so we're going to start with Steve Lowhide. Steve is a professor at University of Wisconsin-Madison, and Steve is very well known for his work on eco-hydrology, particularly the interactions of vegetation with shallow groundwater-dependent ecosystems, lateral subsidy, hydrologic flow on ecosystem patterns, surface water-groundwater interactions, and among others. But today, Steve will focus on the upper Midwest, the eastern part of our huge agricultural domain, pretty much the Corn Belt. Where the shallow water table is a defining feature. And it is hard to make sense of the politics of the Corn Belt, but at least today, Steve can enlighten us on the hydrology of this region. Steve, the floor is yours. Thank you.
Can you see my screen?
Yes.
Great, great. Well, thank you, Ying, for that way too kind and generous introduction. I am really excited to be able to kick this off and talk about the interior agricultural region. And I want to start off just by saying that I really took the idea of a perceptual model seriously. And so I'm going to be talking about my experiences living my life here in the region, as well as the research I've conducted, but really also synthesizing and building off of all of the research that's gone on here. I know that you'll be hearing a lot about Wisconsin after this workshop, likely today, but today I am going to focus a lot of my efforts on Wisconsin. So if we look at the agricultural region, we can kind of break it up into different areas. We have the wheat belt to the west. I'm not going to talk very much about that. I'll leave that to Bridget and Kevin. I will be talking about the corn belt just to our south, and also the dairy belt in Wisconsin, recognizing that there is a lot of overlap in these regions. I'm going to first start off, since I'm the first speaker, giving you the 14,000-foot view of the region. And so to do that, I'm just really going to flash up a bunch of maps, mostly so that we can think about this in the workshop later this afternoon. And so the first thing we know about this region is that it has modest topography, relatively flat. We also have an extreme gradient of precipitation with almost a meter in the east and a third of that on the western edge. It is a relatively gradual gradient. And if we think about the timing when rainfall occurs in this region, it is well synchronized with the growing season when we need water for our crops. And if we look at the temperature gradient, very strong north to south gradient that impacts the growing season length, as well as crop choice. And then if we look at the fraction of precipitation that is lost to ET, if we look in the western arid portion, we see that there is a very high amount of precipitation that is lost to ET, and that's of a very small amount of precipitation, so extremely limited runoff. Whereas when we go to the eastern portion, up to a third, maybe a half of the precipitation ends up becoming runoff. So really different hydrologic response. In addition, even when you look at a very fine scale map of the area, you see a lot, the brown color here, of cultivated crops, as well as pasture and grasslands, those yellow hues. But really the landscape actually does have a lot more. There are a lot more remnant pieces of different types of land cover that kind of gets washed out at this scale. And so it's important that we think about that, the functioning of those elements as well. When we look at the EPA, they have level 3 ecoregions, And while this may seem like a pretty large uniform area, it's actually not. We have as high of a density of ecoregions as other parts of the country. And so, each of these do function somewhat differently. And the soils are a big driver of that. We think of agricultural silt loams. Who doesn't love the state Wisconsin soil, the Santiago silt loam? Those silt loams are across Wisconsin, Illinois, Iowa, and Ohio. But we also have some sandier loams in Iowa as well. These other soils, though, you look at Minnesota. Oh my gosh, it looks like a rainbow unicorn got sick up there or something. We have all different types of soils smashed together. And so my point here is that this region is not a monolith. The climate, the substrate, the topography, land use, land management, all conspire to generate a really wide range of eco-hydrologic responses. So that's first point without really any evidence to support that. I am going to now dive into our true tour and start in the driftless area of Wisconsin. The driftless area of Wisconsin is so called because it escaped the major last 3 glaciations. And so as a result, the topography was not smoothed out and leveled. We have a much more well-developed network of streams and higher relief for the region, especially as you get towards the major drainages like the Mississippi. We see that there are broad, relatively flat uplands, and then very steep hill slopes down into valley bottoms, some of which are experiencing restoration. Land use and development in this area started in the early 19th century when European immigrants came and brought European farming practices. They were not accustomed to the relatively steep hill slopes, and particularly not to the strong convective summer thunderstorms that we receive. And so those agricultural practices where they plowed up the hill slopes led to extreme runoff, extreme soil loss, extreme gully formation, and downstream flooding. We look at what happened to the valley bottoms. That I don't think it can be overstated. That amount of soil loss. There's a horse and rider for scale here. In terms of all of that upland soil, it gets transported down into the valley bottoms and created a cultural sediment layer, separated the stream from its floodplain, dried it out the floodplain, enabling agriculture to occur. And until that time, kind of stayed in that state. But restoration activities have involved removing that and trying to restore the eco-hydrology of those bottomlands. But that restoration doesn't do any good unless you fix the problem. And this has been a real success in the region, was the formation of the Soil Conservation Service. Their first effort was in the driftless area of Wisconsin in Coon Valley, creating erosion control demonstration projects, changing the landscape, introducing best management practices like contour cropping, which you can see here along the hill slopes, removing agriculture from some of the steepest, least suitable parts of the landscape, as well as other tillage practices. By the 1960s and 1970s, those practices were really being adapted in the region. And you can see the peak stream flow has a really substantial change in that we no longer see the really extreme events once those conservation practices occur. Those conservation practices also, if you kind of look through this picture, you see the contour plowing, but you also see a lot of forests on the steeper portions of the landscape. Those really also change not only the runoff and the erosion, but the base flow. So you can also see increases in base flow as the snow melt, which is our major recharge season here in the Midwest. So a model of this system involves really layer cake stratigraphy. And if we look at different parts of the landscape, Paul Jacquem and others measured the infiltration. And you can see that on the ridge here up at the top, there's very low infiltration rates, regardless of what the land use is. And that's because of this round tree formation. It sits on top of carbonate rocks. And so long-term dissolution and weathering has created a residual soil that has a lot of clays and low infiltration capacity. So we don't get very much infiltration or recharge in that portion of the landscape. But on the hill slopes, we get substantial infiltration, particularly in parts of the hill slope that are less intensively used and in parts that are forested. It's off the scale here, amounts of infiltration in the forested hill slopes. And then we get down to the valley bottom and we have kind of intermediate infiltration characteristics, but we have a feeding of groundwater through these perched aquifer systems and down into the valleys supporting wetland vegetation there. So my first real point here is it's not only land cover that matters, but also land management, which is a major hydrologic control in these intensively managed regions of the country. We're now going to move a little bit east here and go into the glaciated portion. And we're going to sit right here in Dane County. University of Wisconsin is in the center of Dane County in the lakes, and it sits very close to the edge of the where the maximum extent of the Green Bay lobe of the glaciers, the Wisconsin Laurentide ice sheet, ended. And so the dark green represents the terminal moraines. The light green, which covers the majority of the county, are ground moraines, and embedded within that are outwash plains, kettle lakes, kind of hummocky surfaces, as well as hills that are drumlins that are aligned with the direction of glacier flow. So I'll take you and tell you a story about a lake, two lakes actually, where I spent my childhood. And so here I am on the shore of Crystal Lake as a budding young hydrologist, making stream channels on a sand pile. And here my son is a couple decades later. And it's hard to recognize everything in the picture because a lot has changed. But if I point out these trees, which are the same as these in this picture, the one thing that should be painfully obvious is there's a lot less land and a lot less water between those locations. As you can see, here's the 1937 water surface, and here's the water surface from more recently. Also see how much nearby Fish Lake has gone up during that time. And so both Crystal Lake and Fish Lake were increasing steadily until 2019, when Crystal Lake increased to the extent in which it overspilled its top. And so any additional rise that would have occurred in Crystal was stacked up on top of smaller Fish Lake. And so we saw extremely rapid rises in water levels in Fish. And over that whole time span, over 5 meters of lake increase. Here you can see over on Fish Lake Road, and that's the road I used to take to go to town to ride to work at Dairy Queen. That runs right back here behind these houses, which were not built underwater. And so extreme changes here in this portion of the agricultural region. We can see those not only with water level, but if we look at those lakes with satellite imagery since 1980, as well as aerial photos from 1937, we see that general increase in surface area of these lakes. So this is a long-term trend that we're seeing. And from 2006 to 2018, we mapped out new water bodies flooded portions of fields, new ponds, new lakes that are being born, and found 155 new water bodies in this landscape over a 12-year period. We looked at where those occurred, and they were, by and large, within internally drained basins within our county, and that covers 17% of the land area. If we look at the increase during the satellite era here from 85, we see that the drained basins saw really no increase in water level. It's these internally drained basins where we saw a 50% increase in surface water aerial extent. Why is this happening? Well, the watersheds that we most often work in are well-developed drainage networks, right? We have infiltration that can escape the root zone and become recharge, cause the water table rise, a steeper gradient towards the channel, and more discharge. There's a feedback mechanism by which this is self-regulating. In the internally drained basins, we have infiltration that creates a recharge, that creates flow towards the lake, and then the lake and the groundwater both go up. But that water is stored within this internally drained landscape. So if we look at one of these basins, the one with crystal and fish lakes in it, and perform a water budget, what we quickly see is that precipitation and ET are any imbalance that generates either an increase in precipitation or decrease in ET is what drives the system to change. And because the groundwater flow, the net inflow and outflow of the basin is slow to respond and requires a change in water level state, right? An increase in gradient. That is very little changed in many respects, and there ends up being a very high sensitivity to the amount of storage, the groundwater levels and the lake levels within the watershed. So what causes that imbalance between precipitation and ET? One, in this watershed has been a sustained driver. That is from 150 years ago when we replaced oak, savanna, with deep-rooted grasses and trees to row crops. And those row crops have shallower roots, and so they may become a little more water stressed during dry periods. And they also have shoulder seasons when there's no vegetation within the fields. And so those two differences in the ET have ended up increasing groundwater recharge. So that's the slow long-term push. We have not found a new state from that, but the rate at which we're changing has accelerated drastically because of increases in precipitation we've seen in the region, particularly since 1980. So I want to move now up north to an area that is some ways completely different and some ways similar. And so when we in Wisconsin say we're going up north, that means we're going to a different place, a different state of mind. We're heading to cabins in the woods. And people in Wisconsin argue about when you arrive in the North Woods. Is it a specific highway that crosses the state? Is it a county line? Well, really it is the transition in vegetation, and you know it when you're there. Right? You're moving from what was the oak savanna and is now much the cropland up into the northern forests. That boundary between those two has existed for, since pre-development, and it's called the tension zone. So it's outlined here in this gradient, and it's very well aligned with a contour in potential ET. So this is in many ways a climate-driven boundary that's creating this boundary in the ecotones, and has been always a boundary. Here's the First Nations, the Ojibwe to the north, and the Ho-Chunk and Dakota to the south, which lived with these and were stewards of these landscapes and took care of them differently in the prescribed burning which they conducted. In the northern part of the state, the hardwoods, this is the site of the Northern Temperate Lakes, LTER. And a concept has really stuck here to explain differences in the lakes, differences in lake clarity, differences in lake chemistry, differences in the food webs within the lake, and its landscape position. And it's based on shifting balances of the water budgets of each of these lakes, with those high in the landscape, these seepage lakes, receiving precipitation. They're very sensitive to droughts and changes in precipitation. Their water levels fluctuate quite a lot. As waters move through the landscape, they pick up more solutes, and they also stabilize until you get to the ones lowest in the landscape, which are much more hydraulically connected. There may be streams connecting those larger ones where they may be isolated and only connected through the groundwater system high in the landscape. And so these change water level much less. It's not only the lakes that are affected by this, right? There's always also the groundwater system and the forest in between. We're interested in what the influence of the forest is on the groundwater system and want to know how much water does the forest use for different depths to water, with a kind of conceptual model here showing that there'd be higher water use where there's access to groundwater than where groundwater is deep. And this idea, is one that's very well developed with phreatophytes in more arid regions, but people do not think of Wisconsin forests as phreatophytes or using groundwater, right? Or really being Wisconsin forests really being that water limited. And so, we decided, well, I think we should check that, measure the water level. And what we found were very regular diurnal water table fluctuations. These are ET-driven fluctuations over a 24-hour period where you see drops in the water level during the daylight when the plants are transpiring. You can use this signal to quantify the groundwater use. And so for a single day where we have a well, we can quantify how much groundwater the vegetation near that well is using. And for the entire record that we've collected, we can calculate every day's groundwater use. We have other wells, and so we can do those. And so now these are all the data that we have between 3.5 meter and 4.5 meter depth. And we find that about up to 10% of the days, we see groundwater use when the water table's within that range. And the water level use here, this is just a normalized scale of the groundwater component of ET, is relatively modest. If we look into environments and places where the water table is deeper, we see almost no groundwater use. But if we look where it's shallower, we see this increase in water use and increase in frequency, up to 50% of the days seeing groundwater use. And so what we've changed in our conceptual model that trees in Wisconsin do use groundwater, but not everywhere and not all of the time. A pretty, pretty good rule of thumb is that if it's within 5 meters, the trees may have some access to groundwater. Does this affect the trees? Does tree growth vary with groundwater depth? Do we see more biomass as indicated by tree rings? And so we went, collected tree cores, and for a tree where we have a water level, we can get a normalized indicator of growth. So kind of average growth would equal 1 for each year that we have a groundwater measurement. And so here's all the years of groundwater measurements and the associated ring growth with trees in the vicinity of that well. We had wells that are deeper, and we see that, they're all pretty much a little bit below average growth. But as we go to shallower groundwater depths, we see that in some years, the trees have substantially more growth, up to twice as much as average, when they have access to groundwater, even in Wisconsin, a place that's really not that water limited. And so can we map this? How important is this across the landscape? We took some remotely sensed vegetation index, thing like NDVI or greenness, and have a conceptual model that says, well, how might groundwater affect this? Well, the greenness overall, places that have access to groundwater and are always growing well are going to be greener. Areas that have less access are going to have more variability between wet years and dry years. If we look at the NDVI index, and then if we look at the difference between a known dry period, a very dry period on record, and a wet period, we'll also get a difference that we can map out. With these 3 different indices, we can do a cluster analysis and things break out. And one of the things that breaks out is this cluster number 5, which ends up being the places where the water table's shallow. And so the mean depth of pixels that are green here ended up being, regions where the simulated water table was shallow in this landscape. And so we can see that it's, a pretty important part of these northern Wisconsin environments. So the takeaway here is that shallow groundwater feedbacks alter the water balance. I'm going to move back to southern Wisconsin now and say, well, what does that mean for crops? And so does groundwater affect crops? The conventional wisdom is that shallow groundwater causes waterlogging and must be drained from the landscapes for agriculture. We looked at this and we happened to get an extreme drought, a devastating drought in 2012. And then 2013 started out as a really, really wet year. You can see indications of oxygen stress and waterlogging in this kind of yellowish color here in the field. So how does groundwater influence crop yield? Our model here is that if the water table is really deep, there's no influence. If it's really shallow, we see negative impacts. But in between, there's kind of a Goldilocks where you don't experience oxygen stress and anoxia in the root zone, but you may benefit from some extra water availability. The increase in or presence of shallow groundwater relative to free drainage is something that we call the groundwater yield subsidy. We measure this out in the field, kind of like an eco-hydrologist would, measure everything you think might be important. And what we find here is that if we look at silage and grain yield, and we compare that to blue, the county average, even in this very extreme drought, the year where the water table was shallow, within about a meter of the land surface, silage yield was actually slightly greater than average, and grain yield was just slightly below. When we go a little bit deeper, about 2 to 3 meters to the water level, we see substantial decreases in yield. And when we go very deep, we see almost complete losses in this extreme drought year. During the drought year, we also flew thermal remote sensing cameras over the watershed, collected and mapped ET. And what we see is some areas that even in the beginning of the growing season in June had really low evapotranspiration. These are on 3 ridges that are little terminal moraines, recessional moraines within the field. And when we look at yield as collected by the combine at the end of the season, we see those had very low yield as well. And we could see that the patterns that emerged early in the season really translated to yield in the fall when the crop was harvested. Take that yield map and just normalize it so that we have kind of average yield at 0, below average, and above average yields plotted with red and green. Do that also for a wet year. And we can see some of the patterns are the same, right? Those ridges are low in both years. This area, this outer ridge, this low-lying area is, pretty good in both years, but the center part is pretty low yield in a wet year. So we compare those, just create a plot of normalized yield in the wet year and in the dry year, and Some parts, the pixels that are plotted in green, did well in both years. Some did poorly in both years. Some were kind of about average everywhere. And the ones that are most interesting to me are the ones that did really well in a dry year on this axis, but really low in the wet year. So those are wet sensitive, these blue pixels that are in low-lying places of the landscape. And then the drought sensitive ones, which did well during the wet year, but bad during the dry year. We look at these then and compare them to the water table, the 7-day high water level. And those wet sensitive ones were the areas where the water table was really shallow. And so they were experiencing groundwater penalty. The consistently good ones were in an intermediate zone, indicating that, you know, if we manage to have our groundwater at the right level, we can get kind of the best of both worlds, protection against droughts and protection against wet years. And then the poorest forming ones were the ones that were in, you know, had no groundwater influence. So what do we do to have our landscapes function like this? Well, one thing we do is we install tile drainage. So tile drainage are perforated pipes. You could see one going in here in Marshall, Wisconsin. There's a little bit of pipe there, some here. And so this is getting sliced into the ground and installed at about a meter or so. And when the water table goes above that, it will flow into the pipe and then be discharged into a ditch or a natural stream and removed from the site. Believe that this, you know, it does improve growth and crop yield. It improves trafficability, so you can get the tractors out in the spring when the fields are often wet, and improves soil aeration and soil quality. We have done this in this replumbing of the landscape in a really massive way. And so particularly here in the Corn Belt, we have very, very high percentages. Browns are over 50% of the land has been tile drained. That estimate from USDA is that in the US we have 53.2 million acres of tile drainage, mostly in this part of the country. That's mapped here. And that area is about 1.5 times of tile drained land, 1.5 times the area of Wisconsin that's been tile drained. Now, I did this kind of late at night, back of the envelope last night. But if you assumed a 55-foot spacing, that would be 800 feet of tile drain per acre, which is 8 million miles of tile drain, which I think would wrap around the world 300 times. So this has major hydrologic effects. It removes excess water from the root zone. Because of lower antecedent moisture levels, we have higher infiltration, which means we get lower runoff, lower peak flows and flooding, but increased watershed base flow, decreased groundwater travel times because we've made those subsurface flow routes much more efficient, and increased annual runoff volume, and very importantly, increased in-stream nitrate concentrations. And so this has led to a lot of export of nutrients to the Gulf of Mexico and the dead zone. We also do irrigation. You might say, do you do any irrigation in this region? Yes, but not everywhere. If you look at the irrigation wells, those are in green. Really, they're here in the Central Sands region of the state. You know, there's some in other sandy parts, particularly here around the floodplain, the Sandy Wisconsin River floodplain, but mostly in the Central Sands, home to Wisconsin's potato growing region. Bridget's going to talk about this a lot more, but I want to draw one contrast. The amount of groundwater depletion we see is really pretty modest. Just a little over 1 meter here at the center of this bullseye. Nevertheless, because this is a flat landscape, very high hydraulic conductivity media, that's enough to dry up streams, reduce base flow. to the extent that the Little Plover River in the Central Sands was literally the poster child in 2013 for America's most endangered rivers. And so my final point here is that agricultural infrastructure, both tile drainage and irrigation, is intended to change the hydrology of the landscape to make it more suited for agriculture, and it works. But if we're going to model this region effectively, we have to include that infrastructure and its changing management. So with that, I want to thank especially Dom Ceruzzi, Sam Zipper, Harold Barker, and Eric Kostelik for their works on parts of this, as well as our funders, and happy to take questions.
Okay, anybody have any questions? Please put them in the Q&A. Okay, I see one showing up. Does the extensive use of drainage tile in the shallow regions alter deeper groundwater paths? And if so, how?
Yes, so without having studied that myself, I can say yes, it does, in that, you are taking water that would be normally moving through the deep groundwater paths, and you're short-circuiting it. So there's a lot less movement of water at depth, because a lot of it takes kind of the first freeway exit ramp it can and leaves the system. And so the residence times are drastically changed on average.
Awesome, thank you. And we have a couple more coming in. From Victor Gallo says, thank you for this presentation. Have you determined the base flows related to restoration areas in the basins? And was 4 annual base flows?
For restoration, did you say?
It says, have you determined the base flows related to restoration areas in the basins?
Yeah, so a lot of our work has been done in riparian wetlands and fens that are groundwater discharge areas. And so because those are groundwater discharge areas, it's really the groundwater that's supporting the vegetation community, and those are not parts of the landscape that are really recharging the groundwater system.
Gotcha. Okay, thanks for that.
I will say that some of the, if you're thinking about other types of restoration, like prairie restoration or conservation reserve program that has been implemented in the driftless area on the hill slopes, a lot of those are practices that change the agricultural lands and are thought to rest the agricultural lands and redevelop the soil health and structure after tillage. And so those restoration projects do increase infiltration.
Great, thank you. Next question is, won't the groundwater runoff be needed during a drought?
Yeah, so we, actually our problems in Wisconsin are limited times of drought. Most of the time, water quality is our first issue, and then flooding would be our second. And so it's relatively limited drought planning that we have. But we also do have, are lucky to have a lot of groundwater systems. And so we do get a lot of base flow. That kind of, makes our specific system more resilient towards dry periods.
Makes sense. Next question is from Wouter Knabben. Hi, Steve. Amazing talk. It seems in much of what you're saying, landscape structure and resulting groundwater connections play a large role. Could you comment a bit on the traditional way of delineating and modeling catchments based on surface topography only? To what extent can such an approach be effective in landscapes like this?
That's an awesome question. Yes. So, we usually, as hydrologists, like to wave our arms and say, the watershed divide, if you have two streams and you have some topography in between, your watershed divide in the mounding between those two streams is probably going to be roughly coincident with your surface watershed boundary. And so, you assume no groundwater inflow or outflow. That is not the case in these flatter landscapes, particularly the high hydraulic conductivity sands and the internally drained basins, right? Those internally drained basins, the watershed is a circle. And we do have more precipitation than ET across the landscape. About a third in my part of the world, about a third of the water is runoff, right? So only 2/3 is going to leave through ET. The rest has to find another way out. And so those internally drained basins, it has to be through the groundwater system, which is continuously working, but not that efficient.
Thank you. We have time for a
The
few
other
more.
places, it's more likely to be true. Like, so in the driftless area, if you have, deeply entrenched streams that are connected to the aquifers, then you likely will have mounding in between that would be roughly coincident with the watershed boundary.
Makes sense. Thank you for that. We have several more questions. We have time for a few more here. This one is from Mohammed Uzar Rahil, and he asks, how have you incorporated anthropogenic activities into the model? As the first part of this question. There's multiple parts, so I'll let you answer that one first.
Yeah. So it depends on, I guess whether you're talking about the perceptual model or the modeling that we're doing. But for instance, part of this Fuscapes, this is an Infuse project with Chris Kucharik. And so we're modeling the watershed response of the upper Mississippi with AgroIBIS, a biophysical model. And in some inset areas, we're incorporating those groundwater dynamics, but we have to really consider, what is the crop that's being planted? What is the phenology of that crop? What are the timing dates? And so those are things that have to be put into the model. And then we consider scenarios of what if there's a policy change? For instance, what is the effect going to be of that policy change? An example that's happened is the renewable fuel standard, where we shifted to trying to produce ethanol, and that had a major impact. It was an unintended consequence, but not unpredictable consequence of creating a substantially greater demand for corn. And so I think it's about 40% of our corn is going towards ethanol. And so that caused a shift in land use dynamics. And so marginal lands that had been out of production, perhaps on like hill slopes, like in the driftless area, went back in. And so that's an effect that we see of land use, right? Land use change related to a policy. And so we're considering now, what if we targeted certain landscape elements for conversion to a different land use type, for instance, semi-natural areas. Yeah, great question.
Yeah,
but it is hard to do. We have also implemented in that tile drainage, which is hard to do at a large scale, right? You can't implement every single tile drain. We have a hard time knowing even which fields are tile drained, although some work has come out on mapping it up from what we know about tile drainage from census reports, interviews of farmers of how much of their land is tile drained, to trying to say, okay, where is the land that's tile drained? Yeah, but it's hard to upscale that into models.
Yeah. We are out of time for questions. We need to move on to the next speaker. We have several more here, Steve, so we will provide those questions to Steve and try to get answers to the group, sent out.
Great.
But
Thank you
you
very
so
much. I look forward to
Steve.
reading them. I've seen things popping up, but haven't been able to keep track.
Yeah, you've gotten
Thanks.
a lot of questions. So yeah, definitely spawned a lot of thoughts, and it was a great presentation. So thanks a lot for that.
Great. I'm looking forward to the next ones.
All right. All right, we're moving on to the next speaker, and I think it is Martin who will be introducing Dr. Shook.
Yes, very good. It's my pleasure to introduce Dr. Kevin Shook. Kevin has been a researcher at the University of Saskatchewan for, gosh, Kevin, what is it, 20 or more years?
17 years.
17 years, and he's been making fundamental contributions on understanding the fill and spill dynamics of prairie potholes. Kevin, a little known fact, likes to bike to work every day, including when temperatures are -40. And I'm not giving the scale there because, when it's -40, it doesn't really matter if it's Celsius or Fahrenheit, it's cold. I think the process understanding that Kevin's been able to develop in the prairie pothole region over the last couple of decades has really advanced our understanding of the system. And it's shaping the development of models, especially in the next-gen system, and I'm really looking forward to hearing Kevin's presentation. So please welcome Kevin, and thanks a lot, Kevin, for joining this webinar. I'm looking forward to your comments.
Thanks, Martin. Make sure everybody can see my screen here. Is it okay?
It's perfect.
Everybody can see. Okay, great. So I'm going to be talking about the Canadian Prairie Pothole region, which is part of the overall prairie pothole region, which extends from the Canadian states down through the US. And being from Saskatoon and working in Canada, most of my work is going to be focused on the Canadian prairies, but the same sorts of processes exist in the US, although of course the details will be slightly different. The Canadian prairies are the southern regions of the provinces of Alberta, Saskatchewan, and Manitoba. And the climate is cold and semi-arid. The mean annual temperature for Saskatoon was 2.6 degrees Celsius between 81 and 2010. The annual precipitation increases from west to east. In Saskatoon, it's about 450 millimeters per year, a third of which generally falls as snowfall throughout the region. And although that seems like a small fraction, we're going to see that it's hydrologically critical to the region. The region is primarily agricultural, mostly dryland farming. The only significant irrigation in the region is in southern Alberta, where there's quite a lot of irrigation. There's talk about increasing it in Saskatchewan, but right now most of the agriculture is dryland, and anywhere there's irrigation in the region, it's all from surface water. As far as I know, there's no significant groundwater irrigation. The main crops are grains, wheat, barley, oats, etc., canola, and pulses, legumes. The region was settled relatively recently. Manitoba only became a province in 1870, and Saskatchewan and Alberta became provinces in 1905. And as a result, some of the anthropogenic influences are different from what happened further south with earlier settlement. When we talk about the Canadian prairies, it's important to understand what type of hydrology we're dealing with. Throughout the prairies, there are a couple of large rivers, the North and South Saskatchewan, and their tributaries. And these are really exotic to the prairies. The flows come from the mountains and the foothills. Almost none of the flow is contributed within the prairie ecozone. These aren't prairie rivers. In that map, you can see the province of Saskatchewan, and the blue line here that's the North Saskatchewan, South Saskatchewan. They join together to form the Saskatchewan, and the width is proportional to the mean annual flow. And you can see there's no change in the mean annual flow through the province because almost nothing comes into the rivers from the prairies. So these aren't prairie rivers, they're essentially canals which take water from the mountains and the foothills to the ocean. So when I talk about prairie hydrology, I'm not talking about those rivers. I'm talking about the basins of small rivers and streams, or as you're going to see, maybe no stream at all, because that's also something that we deal with in the prairies. We all stand on the shoulders of giants, and in the case of prairie hydrology in Canada, the most important person was Don Gray. He was my supervisor as a grad student, and he's really the father of all Canadian hydrology. He started investigating the hydrology of the prairies in 1961, and by the early 1970s, he did some of the first hydrological modeling in Canada. And he found that every model that they tested failed completely. And that's why he famously said that the Canadian prairies are the graveyard of hydrological models. Now, that was certainly true, but we've been doing work since then. Don did so much work, and we've all been doing other work since then. And we now can model a lot of the processes on the prairies. But it's important to understand that because the region is unusual, that models that were developed elsewhere just don't work very often because they either don't include the important processes or they don't do a very good job of explaining them or modeling those processes. And so that's an important point to bear in mind when you're dealing with this region. It's a difficult region to model. The first thing that comes to mind is that it's a cold region, yes. And so it has very many cold region hydrological processes, which are absolutely critical to model. We're going to see that the hydrography of the region is also very unusual. We don't have a lot of data. There's not a lot of flow data. The region hasn't been settled that long. Our basins tend to be quite large, so we don't have a lot of gauging sites. There's not a lot of meteorological data in many parts of the prairies because it's Canadian prairies, because it's been very sparsely settled and has not been settled for a long time. So we don't have a lot of meteorological data. And unfortunately, in Saskatchewan, there's not a lot of LIDAR data. There is in Manitoba and Alberta, but not in Saskatchewan. The climatology and the hydrology is highly non-stationary. And because it's such a cold region, climate change is uniquely important and is uniquely affecting us because it's not just the amount of precipitation, it's how it falls and what happens to it, which is all affected so much by temperature. Everything changes at around 0 degrees Celsius. We have changes in vegetation because of changes in agricultural practices. Cropping practices have changed over time and will continue to change. And we're going to see that there have also been changes in hydrography. So all these sorts of things make it a very difficult place to work in. I mentioned that it's a cold region, and I want to show that historically, most of the peak flows in the Canadian prairies have been caused by snow melt. So although only about a third of the precipitation falls as snow, most of the stream flow is caused by snow melt. So you can see here, these are all of the uncontrolled prairie stream annual peaks between 1919 and 2018, plotted by month. And you can see most of them happen in March and April because that's when the snow melts. The snow starts accumulating in October, November, and the snowpack melts in March and April, and sometimes even into May. In June and July, we can get some rainfall peaks, but historically, most of the stream flow peaks and most of the stream flow volumes have come from that 1/3 of annual precipitation, which falls as snow. This is a creek that we've studied a lot called Smith Creek. It's in southeastern Saskatchewan. You're going to see this again. And these are the annual hydrographs from 1975 to 2020. And there's a couple of things to see. First of all, there's not much going on. This is a basin of over 400 square kilometers in size. And you can see some years there's almost no flow. In most years, you get one blip in the spring. That's when the snow melts and it runs off. And the amount changes from year to year. It looks like it's increasing. We'll come back to that. But you can see most years you just get a single blip and maybe another one in the summertime if you get a big rainfall event. Notice it says virtually no base flow. Yeah, most years you can see it's flat. There's after the spring freshet, there's not much going on. So there isn't much in the way of base flow, and that is very typical of streams in the prairies. Base flows are usually non-existent. They don't really exist. And we're going to see why. So the hydrography of the Canadian prairies is weird. It's not like most other places. And there's a few reasons for this. First of all, the region's very dry. We sit in the rain shadow of the Rocky Mountains. The precipitation generally increasing as you go from west to east, but it's dry. It's semi-arid. It's flat because it was scraped flat by several glaciations. And it's new. It's only been 10,000 years since the last deglaciation. And because of this, there hasn't been enough water flow, energy, or time to generate conventional drainage networks. We just don't have streams in a lot of the Canadian prairies. Also, because it's a post-glacial landscape, most of the region is underlain by deep deposits of glacial till. They could be 50 to 150 meters thick. And this stuff is natural concrete, is largely impermeable. So infiltration happens not to be a big deal in very many parts of the Canadian prairies. It's a small factor. And that's why we don't see base flows in many places. So this is what a typical prairie basin looks like. This is just a picture from Google Earth. The lines that you see are grid roads. They're a mile apart. And yeah, you don't see a stream in this picture, do you? No, not at all. Not a single stream channel. What you see is thousands upon thousands, or if we zoom out, millions upon millions of depressions known as potholes or sloughs, as we call them in Saskatchewan. And that's what we have instead of streams in much of the region. This is what we're dealing with. You can see how flat it is. So we have these depressions all over the place, and these have major effects on the hydrology of the region. These actually control a lot of what is going on, and they make it very difficult to model, and it could not be done until quite recently. So if you look at a slough, this is a paper done by Masaki Hiyashi, you'll see that we have a pond, which is the water sitting in a depression. There is soil underneath the surface, and that soil, it can be quite thick. It's where the crops grow. It's underlain, generally speaking, by glacial till, which for all intents and purposes is impermeable. We divide the landscape into the wetland part and the upland. The upland is where the runoff happens into the pond, into the slough. And you'll notice that there's a willow ring around the outside. There's often a ring of shrubs which have roots that can get water from the pond. And you see those around many large sloughs. The willow rings are important because they also help trap blowing snow, helping to increase the amount of water in the depression. This is an aerial picture of Saint Denis Research Basin. This is just outside Saskatoon. And you can see the uplands, the wetlands, the willow ring around the outsides of some sloughs there, the ponds. And it may be amusing to notice, but note that this is actually considered to be a pretty hummocky landscape in Saskatchewan. Although it looks macroscopically pretty flat, this is fairly hummocky. This is one of the locations that's been studied for a very long time in Saskatchewan. If we zoom out a little bit, this is a map that was produced from data that was put together by the Prairie Farm Rehabilitation Administration in Canada, which was a federal agency. And they identified the areas which they deem as being non-effective. And that means that these areas which are in red do not contribute flow to any kind of a stream at least 1 year in 2. And you'll see that red area that you see here coincides exactly with the prairie ecozone in Canada. And it extends down to into the US as well. So what they are saying is that this landscape here does not contribute at least 1 year in 2. But that means that sometimes it does contribute. And that's the difficulty that we have to deal with. And it makes it very hard to model in this region, because you have to figure out how much of your basin is contributing flow at any time. The problem is that this contributing area is dynamic, and it depends on the states of water storage in the depressions. So this is something that is not dealt with by most hydrological models. They can't deal with this complexity. So this phenomenon is called fill and spill. And what happens is that when a slough reaches its sill level, it can spill to the next slough. And that can then spill to the next one, and then the next one, and the next one, all the way across the landscape. So this is a very dynamic sort of a thing that happens. And this is a picture of Smith Creek Research Basin taken in the spring of 1995, when you can see what happened here. So all the depressions are filled. It looks like an inland sea. Looks like you could canoe all the way to the horizon. Somewhere in this picture, there is actually a stream channel. And so any runoff that's happening here can make its way eventually over the landscape into a stream channel. But of course, this is an extreme case when everything is filled up. That's not always the case. So to make things more difficult, we know that the contributing fractions of basins are hysteretic with respect to the storage of water. And so this makes modeling even more difficult. Similar problems exist for lakes in the Canadian boreal forest in the Northwest Territories. This is actually where the term fill and spill was coined by Spence and Wu in 2003. So this phenomenon does exist in other landscapes, but but those are for lakes. We're dealing on a much smaller scale here. This is a diagram from a paper Martin Clark and I did recently. And this diagram shows why this hysteretic relationship exists between the storage of water in depressions and the contributing fraction. So if we look here, this graph plots the fractional contributing area from 0 to 1 on the y-axis, and the fractional depressional storage from 0 to 1 on the x-axis. And if we start at point A, in this example, this slough is completely filled. And so if any further water runs into it, it will contribute water to the stream channel. And so we have some contributing area and some storage of water in the basin. Note that there's water stored in these two sloughs as well, but they aren't filled yet. So they can still accept more water. They do not contribute any flow to the stream channel. If more water is added from rainfall or runoff, then this slough is now filled. And so any further water going into this slough from runoff or rainfall will then contribute flow to the channel. And so we are at this point B, where we have increased the amount of depressional storage, and we have an increase in the fractional contributing area. We still have this slough, which is not yet filled, but it contains more water. If we add more water to the system so that all the sloughs are filled, then we reach this point where we are at 100% contributing area and 100% of the depressional storage. We will reach this point. That only happens infrequently. What happens very often is we have evaporation. And so because evaporation affects all of the sloughs, all of them lose water, and none of them is filled completely. So any addition of water would go into the sloughs. It would not reach the stream channel. So the contributing fraction drops immediately to 0. So we have this space in which we are operating, where water is being added and removed and added and removed and added and removed from the system. And so we move around in this semi sort of triangular space here with an infinite number of hysteretic loops. And so this is very difficult to model. You can't use any type of single valued function. It won't work. It's been tried. You have to deal with the fact that you've got this complex hysteretic system. So I mentioned the hydrology is complex in the region. And for operational hydrologists or people trying to model things, modeling is very difficult, not just because of these individual processes, but also how they all come together. And if we take a look at a histogram of annual peak flows for any of the basins in the prairies, you find that the flows are very, very highly skewed. And what's interesting is many of them fit Pareto distributions, as this one does. So this is Many Berries Creek. It's one of the longest gauged records in the prairies. And you can see most years the annual peak flow is very, very low. But every once in a while, you can get a very large annual peak flow. It's extremely skewed, but it has a very heavy tail. And this makes dealing with these sorts of events very difficult. They're hard to model, and they're also hard to design for. And what makes it tricky is you have to incorporate all kinds of different processes in order to get the right result for the right reason. Now, you remember I said that historically, most of the peak flows were caused by snowmelt. And if we look at our annual snowfalls in the prairies, they invariably fit normal distributions because of the central limit theorem. So these are the annual snowfalls or precipitations for Saskatoon from November to February, from 1900 to 2007. And you can see, yeah, it fits a normal distribution very well. So if our precipitation or if our snowfall is fitting a normal distribution and our stream flow is fitting a Pareto distribution, how do we get from this to this? And that is one of the central problems of prairie hydrology, is to deal with these extremely skewed distributions of our stream flows. The answer is that there are 3 transformations which contribute to the probability density function of prairie spring stream flows. And we have a paper on this. And the 3 transformations are in order: 1, the accumulation of the winter snowpack; 2, the spring runoff from uplands; and 3, the effects of the depressions. And I'm going to talk about all 3 of these things because you can't get your stream flows correct in the prairies unless you model all 3 transformations, and you have to model them properly. You can't take shortcuts. So the first transformation is from the snowfall to the snowpack. And in many cases, people just assume that the snow on the ground in the spring is just what falls from the sky during the winter time. That is not true at all in the prairies. So this shows some data from central Alberta. The pink is the kernel density plot. It's like a histogram of the March 1st total snowfall over the winter, and you can see it's like a normal distribution. And the blue is from snow surveys that were done, and you can see that a couple of things have happened. First of all, the mean is greatly reduced. Oh yeah, so there's a lot less snow on average on the ground by March 1st than fell from the sky. That's one big problem you have to deal with. The second is that the variance is also reduced. So if you're just assuming that what fell from the sky is what's on the ground, you're already behind the 8 ball. And the reasons for this are two main processes. First is the effects of blowing snow, and the second is midwinter ablation, which can be done by Chinooks. I'm going to talk about these briefly. So blowing snow is critical in the prairies. Prairie snowpacks are shallow, they're dry, and historically they've been continuous over the winter, meaning that there's snow all winter long. The prairies are extremely windy and being very open. We don't have a lot of trees, and so there's a lot of wind that can blow the snow around. And the snow accumulations are highly affected by redistribution and sublimation by blowing snow. And this means that if you're modeling this, you have to include aerodynamic connectivity amongst landscape units, because the snow will erode from places like the tops of hills or where the surface roughness is low, and will accumulate in the bottoms of depressions or where the surface roughness is higher, like in those willow rings that you saw. So you have to think about the landscape connectivity in a different way in the prairies than in other locations. And blowing snow is being strongly affected by climate change. So one of the things you might not think of is that as the snowpack ages, the snow crystals will grow together, and you need higher wind speeds in order to move the snow from place to erode the snow. So one of the that's one of the other things that you have to deal with. And also, if it gets warmer, the snow will get sticky and be less likely to blow. So these are things which affect the blowing of snow. Another thing that we have in the prairies are what are called Chinooks. These are fast, dry, warm winds, also known as foehn winds, which are caused by adiabatic heating of the winds passing over the Rocky Mountains. They're found in southern Alberta and southwestern Saskatchewan. And these were not understood for a long time. It was believed that they were causing sublimation of snow on the ground, but this was actually shown to be true by Matt McDonald in 2018. So this is something else we have to deal with, and these can have very strong effects on the amount of snow that is present on the ground at the end of the winter. The second transformation is from the snow water equivalent to the runoff. Now, everywhere else people talk about runoff as being stream flow divided by basin area. That's not what I mean. I mean the water that is running off the surface in the spring when the snow melts. And this transformation is dominated by infiltration to deeply frozen soils. So you might think that the soils are frozen, the snow melt just runs off. That's not the case. A lot can infiltrate. So here you see measured data from Swift Current Saskatchewan. In pink, you have the kernel density plot of the peak snow water equivalent, and in blue, you have the runoff. So there is less runoff than peak snow water equivalent. So the mean decreases and the skewness and the kurtosis increase. We're getting that heavier tail that I mentioned. It's important to note that the melt is driven by solar radiation in the prairies. It's not driven by air temperatures. This plots the change in snow depth versus air temperature from south of Saskatoon. So this is the daily change in snow depth in millimeters plotted against the maximum daily air temperature. You can see that the R squared is 0.05, meaning that your maximum daily air temperature only explains 5% of the change in snow depth in the spring. In other words, the melt is driven by solar radiation. You can't use a temperature index model in the prairies. It doesn't work. I mentioned the soils are deeply frozen. Yes, they are. So this is soil temperature data collected at the same place. This is at 160 centimeters deep. And you can see that by February, the ground is frozen at down to 160 centimeters. In fact, the soil can freeze down to 2 meters or so in the wintertime. So it freezes very, very deeply. And because of that, it behaves very differently from unfrozen soils. Notice that the temperature starts rising in April. That is due to infiltration of meltwater, which winds up releasing latent heat inside the soil. as it thaws its way in. So infiltration of frozen soils is much more complex than unfrozen. The ice blocks the pores, reduces the pore diameter. That reduces the hydraulic conductivity. It also increases the matrix potential, the suction. To make things complicated, the freezing point of water is depressed by the matrix potential, which depends on the ice content. So all this is very complex and highly nonlinear. And then everything changes when you get melt and infiltration, with energy being transferred amongst the different phases. So it is a very complex system, and you can't take shortcuts with this. You have to model the infiltration to the frozen soils, or you're not going to get the runoff correct. And then the third transformation is the routing through the depressions due to the fill and spill that was talked about. And we showed that the greater the storage upstream, the more skewed is the discharge into a depression. So these graphs show data from Saint Denis, and for 4 different sloughs. Pond 2526, this shows the kernel density of the inflow to the pond. This pond didn't have a lot of depressional storage above it, so its inflows are not that skewed. Pond 109 and 50 had more depressional storage, about the same amount upstream of them, and so they are more skewed. And then Pond 90 had a lot of depressional storage upstream of it, and so it's highly skewed. But you notice it's got that heavy tail out here as well. And so this is the third transformation. So in order to get prairie stream flows correct in a model, you have to be able to model all 3 transformations. The other thing you have to deal with is that the prairie depressions are being drained. Most of the Manitoba region has been drained. Most of Alberta has not. There's been less drainage in Alberta. Saskatchewan's somewhere between the two, and it's increasing. And it's difficult to separate the effects of drainage and climate change in the hydrological record. I'll show you what I mean. So this is Smith Creek, which I talked about earlier. And these are the annual discharges from 1975 to 2015. And you can see big increases in the annual discharges. The black lines are Bayesian change points. And so you can see big changes in the discharges, but also there's been a change in the mechanism. So back in the 70s and 80s, it was almost all snowmelt that was causing the stream flows. However, as we get into the 2010s, now we're seeing mixed events, which are rain and snow, or just pure rainfall events causing stream flows. So what's going on? Some of this is due to climate change, but not all of it, because Smith Creek has been heavily drained. So Smith Creek is down here, the bottom right-hand corner of Saskatchewan. And you can see what's happened with the drainage. So these are ditches that have been dug by the farmers. In 1958, there were a few. By 2001, there were a lot more. And by now, pretty much all of the basin has been drained. The farmers have constructed really a drainage network. And this is what it looks like from the air. So you can see what the farmers are doing. They are joining the sloughs together, connecting them together to get the water off their land. They want to get the water off their land so they can get on the land more quickly. Also, because farm equipment is so big, they don't like to turn around. So it's more efficient for them. But it's also controversial. You'll notice that this area up here is not drained. That's because that land is owned by Ducks Unlimited, and they want to preserve the wetlands for waterfowl habitat. And so this is a very controversial thing that's happening in the prairies, where the farmers are reaping the benefits of drainage, but there are environmental costs associated with it. Another thing you have to think about is that empirical evidence suggests that prairie surface flow velocities might be much slower than in other regions. Yes, the terrain is flat, but that's not the only cause of it. And we find that hydrological models that we build are often too flashy. It's very difficult to get the models slow enough. We calculated roughness coefficients from rainfall hydrographs for 23 basins in central Alberta and found that basin scale values of roughness coefficients were very high in small basins due to the dominance of overland flow. but the roughness coefficients were extremely high. This shows a response time for a very small basin. This is a sub-basin of Saint Denis. And this is the inlet. The flows go around and come out through the outlet. It's about 1.4 kilometers. And you can see that for this event, it took 39 hours for the peak to traverse that distance. Very, very slow indeed. And this is not atypical of prairie basins. They are very slow to respond. So if you're modeling them, keep that in mind. So one of the implications is that it can be dangerous to use tabulated Manning's N values for small basin overland flows. We found experimentally Manning's N values as high as 5 for the basins that we looked at in southern Alberta. The Manning equation may not even be valid in the prairies because it's based on turbulent flows, and there's some evidence that the flows may be laminar, or at least in the transition zone. Why are these velocities happening? They're not clear. Probably it's influenced by the crops because we're dealing with subdivided flows, and also the effects of the depressions. And one of the things to think about is that in any case, as the farmers drain the depressions, the basin response times will change because you'll be going from overland flow to channel flow. So that's also difficult to deal with. So in summary, it's necessary to correctly model cold region hydrological processes to get the right results for the right reason in this region. It's also necessary to correctly model the variable contributing fractions of prairie basins. And neither of these is very amenable to calibration with stream flows because hydrological processes are non-stationary because of climate change, and depressional storage is non-stationary because of drainage. And I mentioned earlier that our gauged prairie basins are really quite large. And one of the problems with calibration is that you may have very different amounts of depressional storage in different parts of a basin. And so if you're depending on calibration, it's not going to reproduce that at all because you're going to have different parts of the basin responding very differently at different times. So that's all I have for my talk, except to say, to show you go back once more to Smith Creek and show you what's going on during the year. So in the wintertime, we have snow accumulation, redistribution, sublimation, and ablation of the snowpack. Happens in the winter. In the springtime, we have our snow melt, infiltration of frozen soils. We have runoff, fill and spill. We have rainfall in the summer, infiltration, evapotranspiration, ponds filling and emptying. And all these processes are happening without any information in the hydrograph. You don't see the outputs of all these things until the springtime when the snow melts, which makes it really tricky. So my perceptual of the model of the Canadian pothole region is to show that there are basically 2 different hydrological cycles. We have a winter hydrological cycle and a non-winter hydrological cycle. In the winter, we have snow, the snowpack accumulating, being transported, sublimating, deposited. In the spring, we have our solar radiation-driven snow melt and infiltration of frozen soil, followed by some runoff. We will then get fill and spill, and that's complicated. So here we have a small slough, and if it fills up, it will probably spill into this large slough. But if both of them are then joined together and the water level reaches this level, then the fill and spill may go that way. So it's a very, very complex system of processes that we have to deal with. So that's all I have for mine, and I've included the references here.
Excellent. Thank you so much, Kevin. That was a really great presentation, and that really helped me understand. I've heard a lot from Martin and colleagues about the prairie region, but this really helped to understand the situation there. So we have a couple of questions starting to come in. And while you're all get your questions into the Q&A, the first is in the image of St. Denis, I saw that there were some roads that seemed to act as dams. Can you describe the impacts of roads on hydrologic processes?
Absolutely. In fact, that's something that's absolutely critical because of there's a road every mile or so, and it is a dam. Now there are culverts in them, but the culverts are often not sited very well, and they often fill up with trash, apparently dead skunks as well. They like to nest in them. So yeah, what you have is a leaky dam every mile, and that is almost certainly part of the reason why we have very slow responses of prairie streams. And it's tricky to model because you have to include that depressional storage of the water upstream of the dam caused by the road.
I could see that. Yep. And next, in contrasting your presentation with Steve's presentation, I noticed that you did not have groundwater flow paths in the connection between ponds. Can you explain?
So remember that we're sitting on top of deep glacial till, which is 150 meters deep. Now there can be some connections between ponds, between sloughs, yes. So you can, if you there can be flow through the soil layer sitting on top of the till, or even through the top of the till if it's weathered and cracked. And so you can have some shallow surface or shallow groundwater connectivity between them, but it tends to be small amounts. Also remember that the small depressions, small sloughs will empty very quickly. So the deep ones can hang around for several years, but the small puddles are gone in a week or so. And so you're not going to get any connectivity there. So yes, there can be some connectivity at the near the surface through the soils or perhaps through cracked till, but it tends to be a small amount. The infiltration through the till tends to be very small. Masaki Hiyashi did some work just west of Calgary where the tills are very thin, and he found 3 millimeters per year of infiltration, which is within measurement error.
Very interesting. Next question is from Wouter. Hi, Kevin. Thanks for the talk. When farmers dig ditches to connect potholes, is there enough natural relief in the landscape to actually make the water move downstream in some sense? Or does it just create more storage in place? Is there anything going on? Oh, I'll let you answer that first part.
Yeah, it seems like there is. There is enough, even in a place like Smith Creek, which is flat as a tabletop, there is enough. Now it flows slowly through those sloughs, but yes, there is enough natural relief, it seems, for the water to flow through there. Yes.
And then the next part is there anything going on with mills to control the water level in the ditch, like you might see in a Dutch landscape?
Oh, you mean like pumping or anything like that? So sometimes rural municipalities will pump water from one side of a road to another or something like that, trying to get water through. What happens is that the culverts tend to, as I said, to plug. They can get plugged with ice and trash, and they are often cleared out in the springtime or just in anticipation of the spring freshet to try and get the water through. But I've never seen a windmill, no.
And then one last part to that. Can you give us some sense of soil depth above the till?
The soils are quite deep. So wheat likes to reach down a couple of meters. So wheat roots will go down like 1.6 to meters or so, and it does. The crops don't like to have wet roots. So the soils you can find several meters above the glacial till in a lot of places. So we have the soils in Saskatchewan are really very high quality. They were formed over only 10,000 years, but it was grasslands. And so they tend to have a lot of organic matter and to be fairly deep. But underneath them is the till usually.
Gotcha. Awesome. Any more questions from the audience? Those were all questions from our panel. Going once. And if not, if you still have questions, throw them in the Q&A and we'll make sure we get those to Kevin so he can answer them at a later time. But thank you very much, Dr. Shook.
Great.
And we will move on to our next presentation. And Ying, you are up to introduce Dr. Scanlon.
Before we do that, I'm sorry, Dr. Scanlon. We have a
Oh, we have a
5-minute break on the agenda. So get yourself some coffee, do a little stretch. We will return here at 11:50 Eastern. So 10 till. Thank you very much.
Sorry, I jumped the gun. I was so excited.
I can't hear anybody, but maybe.
Hi,
Oh,
Bridget, can you hear?
yeah, now I
Okay,
can.
good. Yeah, you need to
Yeah.
test your sound. Good idea.
So I have a video, but I don't know if it's going to play on the gray stuff. So
It should be, you know, you have to share your screen.
right.
Yeah,
But will I wait to share that now? Will I share that now
you
or
can
wait?
share it right now.
Okay.
I just gave 1
Well,
minute for the panel to come back.
Okay, let's see. I just want to. Oh no, wait a minute. I think it's this one. So let's see if you can.
Gravity. It's everywhere.
Can you hear that?
It's the force.
Yes.
Okay, great. Okay.
Did
That's
you
all
do
I wanted to.
that? Did you do the cartoon, Bridget?
No. It's NASA.
Ah.
So, but yeah. So I will share the screen that I'm looking at you with, because when I make my screen full screen, it always shifts to that monitor. So, but anyway.
All right. Yeah, it was easy enough, so we can go back. Let me know, Julia, if you think we should start.
I think we're good to go.
All right. It is my great pleasure to introduce Professor Bridget Scanlon. And Bridget is a professor at UT Austin Jackson School of Geosciences. And Bridget is worldly renowned for her synthesis work on groundwater recharge around the globe in all kinds of climates and geology. But she really tackles a very wide range of water resource problems concerning sustainability under two forces. One is climate extremes, such as droughts. And secondly, the human overexploitation, such as groundwater pumping, large-scale groundwater pumping for irrigation. So today, Bridget will focus on land use and climate drivers. Those are the two drivers have been in her theme of understanding water resources. Today, she will talk about particularly large-scale groundwater pumping and irrigation for the irrigated agriculture, which is probably our largest groundwater use. She will not only focus on Great Plains, but also extending further west, where irrigation was a major regulation of the hydrology, pumping from groundwater. So with that, Bridget, thank you for joining us, and the floor is yours.
Okay, thanks. I share my screen. Okay. Thank you so much, Ying. I really appreciate this opportunity, and it gave me a chance to review work that I hadn't thought about for quite a while. So that was fun. And I greatly appreciate the earlier presentations, Steve Lowhide and Kevin Shook, because they really set the stage. And as Ying mentioned, I'm going to talk about climate and land use drivers and water resources, and talking about GRACE satellite data, and also a little bit broader discussion on modeling also, because we have done comparisons with global models a little bit. So this is the outline of the presentation, and let me see if I can hide. Okay. Hide the, yeah, right. So this is the outline. I'm going to talk about GRACE water storage monitoring, and that gives us a large-scale view of what's happening in response to climate and land use. And then we did some comparisons of GRACE with the global models and discussed those very briefly, because this exercise is supposed to help modelers with the national model. And then talk about climate impacts on water resources in the contiguous US, and then land use change effects, and then a little bit about what we're trying to do to resolve some of those issues, and hopefully we'll consider that also in the models. So many of you may be familiar with the GRACE satellite data, JFM Yeti and many others, Matt Rodell and others really evaluated this early on in when it was being launched originally. And it stands for Gravity Recovery and Climate Experiment and consists of 2 satellites. And by monitoring the distance between the satellites, they estimate changes in gravity. And the first mission was from 2002 to 2017. The second is 2018 and is currently operating. And the next mission is projected to launch in 2028, the GRACE continuity mission. So it's a core scale resolution, 500 kilometers, because the satellites are at a high elevation, the resolution is about 350 kilometers. And most hydrologists are a little bit allergic to that, but it gives us a lot of very interesting data. And it also monitors terrestrial water storage, which includes water storage in the atmosphere and the land surface and the deep subsurface, which differs from many other satellites. So this is a NASA video that might be helpful in understanding GRACE.
Gravity. It's everywhere. It's the force that keeps our feet on the ground and the moon orbiting Earth. But where does it come from? Mass. That's simply the amount of stuff that makes up an object. The more mass something has, the more gravity it has. Earth's gravity is constantly changing because something with a lot of mass is moving around all the time. What's moving? Water and ice. If you've ever picked up a bucket of water, you've felt just how much mass it has. It creates a lot of gravity. Using satellites, NASA can measure Earth's gravity like a scale in the sky. By comparing one month to the next, we can track where the water and ice is going. Weaker gravity means there's less water in that spot. This can tell us where a glacier is melting or a severe drought is drying up lakes. And stronger gravity, more water such as in the rainforest in the Amazon. Our scale in the sky even lets us measure water deep underground.
So I really like that video that NASA made and think it's very helpful. And so here looking at trends in water storage globally over the long term from 2002 through 2021 and shown in units of millimeters per year. So these are terrestrial water storage anomalies. So the red areas are where you see declines in water storage and the blue are where you see rises in water storage. So you can see the southwestern US, large declines in water storage, and blue throughout much of the rest of the US over this time period. And then other regions, you can see blue in much of sub-Saharan Africa. And that may be partly because they don't irrigate very much in this region. And then red in much of the Middle East and northern India and North China plain. A lot of that is related to irrigation. And so we also look at the time series of water storage trends, and you can see the Central Valley in California. You can see large variability in water storage, wetted during and long-term droughts, 4 or 5-year droughts, and then some recovery, and then but a continuous decline over the last century and this century. But then you can see the Great Lakes region, the St. Lawrence, increases in storage. So a lot of people talk about water scarcity and running out of water, but really I think it may be managing extremes may be more of a challenge. And I'm not going to talk much about these other regions, just indicate that the Middle East and North Africa, a lot of declines in storage, and the Ganges, Brahmaputra region, large-scale declines. And you can see the Kalahari in Africa responding to natural climate variability. So if we look at, we did an analysis comparing GRACE trends with modeled total water storage trends using global hydrologic models and land surface models. And here I'm showing some of the basins that we looked at: the Amazon, 6 million square kilometers, Mississippi, Okavango, Ganges, and those regions. So how did the global models compare with the GRACE data? And so here you can see the Mississippi. So the GRACE is 3 different GRACE solutions, CSR, JPL, and then global hydrologic models, and then the land surface models. So I think the thing I would like to point out is that there is a lot of discrepancies between the models and GRACE, and also among the models themselves. So very difficult to simulate these large-scale trends. The Amazon, most of the models underestimated the storage trends in the Amazon, and a lot of difference even among different hydrologic models and land surface models. Okavango, this is an internally draining basin, and all of the models simulated just river systems. And we heard earlier from Steve and Kevin, you know, prairie potholes and those things, internally draining systems. So the models lacked that capability. And then human intervention underestimated that. So what we found in general is that the global models underestimated the trends in GRACE, both the declining trends and the rising trends. And some of the modelers suggested that maybe that was related to that the storage capacity in the models was not sufficient to accommodate the large trends. And Sean Swenson did an analysis inverting the models to see how much storage would you need to reproduce the GRACE data, and showing that in some regions up to 8 meters deep soil storage to accommodate the trends. So that was just sort of background on GRACE and models. So now we'll talk about climate impacts and water resources in the US, and with a focus on the High Plains region in the US. So it's fantastic to have the US Drought Monitor, and so always look at that and the time series of that to see how is the current drought relative to previous droughts and stuff. So I really appreciate University of Nebraska providing those. And then USGS Water Watch. So here I'm just showing in January 2017 as an example, you know, flooding in California, atmospheric rivers, and flooding around the Great Lakes region. So we're either the drought or floods. And so how do we manage those? So Steve showed this map earlier from PRISM, and so in the eastern US humid region in the 100th meridian, often characterizing the difference between humid and semi-arid regions. And so in humid regions, we often have diffuse groundwater recharge, and that groundwater then discharges to surface water as base flow. And in the Western US and semi-arid regions, we often have focused recharge, for example, beneath playas in the High Plains that I will talk about, or ephemeral streams recharging groundwater. So it's quite different between these different climate settings. So if we look at the total water storage trends in the US, then in the major aquifers over the first GRACE mission, 2002 to 2017, work that Ashraf Ratib did. So you can see the Southwest US, as we showed earlier, declines in storage. Central Valley region, the Arizona region, a lot of that related to irrigation, Central and Southern High Plains region, and this is in cubic kilometers over the 15-year period. So some people may be more familiar with million acre feet, so 1 cubic kilometer is about 0.8 million acre feet. But what's surprising, increases in storage in the northern High Plains. Oftentimes we think of the High Plains as a single unit and responding the same way, but it doesn't. And then very little change in storage in the Mississippi embayment region, where there is a lot of agriculture also. And the humid regions in the east, slight rises in storage. So if we look at the storage from GRACE, then we can calculate groundwater storage by subtracting the trends from reservoir storage and also soil moisture trends, which are oftentimes negligible over these long timescales. So if we compare that then with storage changes estimated by Lenny Conoco based on regional groundwater models and monitoring data, you can see similar trends in the Central Valley, about 30 cubic kilometers. These are different time periods, 2002 to 2017, and this is 2000 through 2008. But you can see that depicted the High Plains as a single system with large declines, even though his data showed less declines in the northern High Plains. But one of the big differences that they show is the Mississippi embayment region. So the regional model suggested minus 60 cubic kilometers decline in storage, whereas the GRACE data showed very little change in storage. And so, you know, which is correct? you would think that a very detailed regional model may be more correct than coarse resolution satellite data. But we worked with the USGS and NASA and other academics in a Powell research group, and they redid the regional model in that region and found that they were underestimating, the stream network was not represented at a detailed enough scale, and so they were underestimating capture. So when you pump groundwater in humid regions, you can capture surface water or reduce evapotranspiration. And so they have since done airborne electromagnetics, looking at the connectivity of the river with the groundwater. And now the most recent model, the recharge is much higher and stream leakage higher, and groundwater storage decline is much less. And so it's important to look at things from a number of different perspectives to evaluate what's going on conceptually and otherwise. So we also compared the GRACE data in these basins to global hydrologic models. And here I'm showing a couple of the models, water gap and PCR, global water balance, and then an ensemble of land surface models in green. So blue and orange are the global hydrologic models, and green is the land surface model. And so you can see that the global hydrologic models were overestimating declines in storage in the Central Valley. And also in the Arizona alluvial basins. The land surface models that did not simulate any pumpage or human impact almost captured the dynamics better than the global hydrologic models. Again, in the northern high plains, overestimating water storage declines, and in the central and southern high plains. And then a large difference in the Mississippi embayment. So very difficult for these global models to capture what is going on at these scales of these aquifers. So now I would like to talk a little bit about the climate drivers on water storage in these basins. And so here I'm showing the GRACE data for the Central Valley, and the US Drought Monitor time series at the bottom. So you can see increases in total water storage during wet periods and declines during drought. And this drought was 2012 through 2016. And you can see corresponding to the drought. And then the drought almost ended overnight in January 2017 with atmospheric rivers. So very dynamic systems, and very important to capture that in models. So a strong correlation then between the total water storage and the drought monitor data, correlation of 0.91 in California. So a lot of decrease in storage during drought related to irrigation and reduced recharge. The northern high plains, a strong correlation also with the drought, and so fairly dynamic in this region. But in the central and southern high plains, almost much poorer correlation with the drought, because this groundwater was recharged thousands of years ago, as Pete McMahon from the USGS demonstrated with his age dating. And so what we see happening is that during a drought, we see increase in pumpage, and so that amplifies the drought, but not a good correlation with the climate itself. And then in the Mississippi embayment, the drought intensities are much less in the humid eastern US, and we see some variability in storage linked to that, but the drought intensities are much less. So another factor that Steve and others mentioned this morning was the impact of soils on water partitioning at the land surface. And I thought they mentioned that the till was like a concrete, and that was very interesting. So here I showed the clay content of soils from the StatsGo map of the US. And so you can see in the northern high plains, you can see the yellow area is the sandhill region. And I don't know if you can see, if I can show a pointer. laser pointer. So this region is the sandhills area. And then further south, then you've got much more clay-rich soils. So we saw that the water storage increased in the northern high plains in response to wet and dry climate cycles because you have much higher recharge in the sandhills. And then also you've got irrigation. There's a through-flowing stream, the Platte River, that they irrigate. It accounts for about 30% of the irrigation, and that recharges the groundwater also. Whereas here, the groundwater was recharged thousands of years ago, and so you're basically mining old groundwater in this region. So another, it's really nice to look at the stream network. And so you can see dense stream network in the humid eastern US, and you can see these white areas in around the sandhills in Nebraska, and also in the southern high plains, much of Texas region. And this is because there's very few through-flowing streams, and most of the surface water is drained through endorheic basins in playas, which are some, I mean, in shape and format are kind of like the potholes, but they are recharge features. Originally, people thought they were evaporation ponds, and so they discharged waste into them, including the Department of Energy and municipalities, but then realized that they actually recharge the groundwater. So this is really nice to look at the stream network density to evaluate where you've got internally draining systems and where you've got dense through-flowing streams. And so here are a map of playas in the high plains. And you can see playa density is very high in the southern high plains and then throughout the high plains. And but it really, although there are about 23,000 playas in the Texas high plains, they only occupy about 2% of the land area. And Steve Lohide mentioned earlier that the features that he was talking about, endorheic basins, they occupied about 17% of the land area. And so this is a typical image of a playa with drainage into this playa, and then they have clay at the bottom, and so we thought they weren't recharging, but there's enough desiccation cracks and other things that allow groundwater to recharge the groundwater. So we were doing studies for Department of Energy early on, and so one of the things to look at to see if it's a recharge feature or an evaporation system is to look at chloride concentrations. Very simple. So chloride concentrations in soil water beneath the playas was almost zip, and chloride concentration, there was a bulge of chloride built up in the soil profile in between the playas, which indicates that the plants were evaporating the water and leaving the chloride behind. So a very nice proxy for the water movement in the soil profile. And so this is up to 4,000 milligrams per liter chloride in the soil water, and talk more about that later. So here on the left, I showed the soil map, the clay content, and on the right, then I show a recharge map that we developed from groundwater chloride concentrations. And so you can see high recharge rates in the sandhills in Nebraska, and then very low recharge rates in the high plains further south. Because of the clay soils and the evaporation. So Steve Lohide is very experienced in eco-hydrology, and we dabbled with it a little bit early on, looking at these natural landscapes and how recharge occurs in response to wet and dry climate cycles. So very fortunate to get access to lysimeter data from Department of Energy related to the nuclear waste site. And so this is in Nevada, and you can see this one is a bare lysimeter, and there was another vegetated lysimeter. And so I show normalized difference vegetation data maps where the lysimeters are here. And so during a wet period, you've got high NDVI, and during a dry period, almost none. And then this was related to the 97-98 El Nino. And so what happened was the vegetation just took off. It was very opportunistic, and there was no recharge in these natural landscapes because the vegetation used it up. So this is the lysimeter data from the bare soil lysimeter. And you can see this is the 97-98 El Nino event, and a big increase in soil water storage in the lysimeter and drainage in this bare lysimeter after this period. But in the vegetated lysimeter, you can see when the vegetation zaps the water and decreases the storage, and even in response to a very strong El Nino event, the vegetation very quickly removed all that water. So in these natural landscapes, then vegetation is very important in reducing recharge and controlling the partitioning of water at the land surface. So we did age the chloride based on calculating the mass of chloride in the soil profile and dividing by the chloride input from rainfall. And so here you can see in this typical profile with up to 3,000, 2,500 milligrams per liter chloride. So an age of about 1,700 years, 6,000 years, and at the base of the profile, about 9,000 years. So this profile has been drying out since the Pleistocene times. And we also have water potential data showing that there's an upward pressure gradient, and so the soil profile has been drying out over that long time scale. And so we modeled that then. So this is 9,000 years ago during Pleistocene times when everything was wet, matrix potential was close to zero, and chloride was close to zero also. And so you can see even after 100 years, you can see the matrix potential profile drying out the profile and the chloride starting to build up. So you can see over time, and then we were able to reproduce the matrix potential data with this modeling with long-term drying over this 1,000-year time frame and the buildup of chloride. So this is the natural vegetation. So then let's look at the agricultural areas then and what happens when we change those land use from native vegetation, oftentimes deep-rooted shrubs and deep-rooted grasses, to crops with fallow periods. And Steve Lohide mentioned this earlier. So here you can see irrigated areas in the national land cover data. And so the blue areas show the irrigation, the Central Valley, the High Plains, the Mississippi Embayment, the Snake River, and the Columbia Plateau. So large irrigated areas. And earlier today, we were talking about the cropland areas with the limited irrigation in the Midwest. So I'm just going to show a couple of examples. We saw earlier that in the Southwest US, a strong relationship between wet and dry climate cycles and water storage. And so during a wet year like 2010, here I'm showing irrigation, and the light blue is surface water irrigation and the darker blue is groundwater irrigation. So in the Central Valley, during a wet year, about 70% of the irrigation water comes from surface water and about 30% from groundwater. And so 2015, which was a dry, very middle of the drought, about 70% comes from groundwater and 30% from surface water. So humans then amplify the impacts of drought by changing the water source from surface water to groundwater and enhance depletion. So it's not just climate driving it, but also the human impacts using irrigation. So in the Mississippi Embayment region, then you can see it's mostly groundwater, and they're pumping more groundwater than in the Central Valley. But they're not depleting the storage in this region because they're capturing surface water in this humid region where you've got a dense stream network, and decreasing base flow and capturing surface water. The same in the northern high plains. They capture surface water, decrease base flow in the Platte River. So if you look at rain-fed agriculture, as I mentioned, you're changing from deep-rooted native vegetation to shallow-rooted crops. And you can see these are matrix potential profiles through the soil profile. And so you can see there's a wetting front that moves down over time, and then the chloride is flushed out in the shallow subsurface. And these are just different examples of profiles in the southern high plains showing the impact of changing from native vegetation. And so this is the chloride that accumulated under the native vegetation, and then this is the flushing that occurred when they converted it to cropland. And so here you can see an example in this region. And so 5 years, so about 70 or 80 years ago or 90 years ago, they converted it to cropland. And so this is the flushing of the chloride that occurred. And this is the large chloride that built up under native soil condition, native vegetation conditions. And so this is the flux, then increase in flux up to 10, 15 millimeters per year or 30 millimeters per year in this region, attributed to changing to cropland. And so here are the groundwater levels underneath native vegetation in the southern high plains. And so you can see the groundwater is fairly stable over time, not changing very much. Under the irrigated areas, we see large declines in groundwater because groundwater is the main source of irrigation in the central and southern high plains or throughout the high plains. So huge declines in storage from 20 meters to 80 meters. And Ginny McGuire at the USGS does a fantastic job of providing maps of groundwater level depletion since the 80s and puts these out every so often. And this is rain-fed agriculture then. So we see groundwater levels increasing because of the increased recharge under these rain-fed areas. So then if we look at other things that we can do then to try to manage the water resources. So if you think of water resources as just simply how demand and supply change over time and impact storage. And if we're thinking about irrigated areas, you know, and wet and dry climate cycles and how all those interact, you know, are we increasing demand for water, reducing supplies, and then decreasing storage? So how can we change that then? And I'm not sure whether the National Water Model will be considering some of these things, but you know, there are various different approaches that we can consider. But I'm just going to talk a little bit about managed aquifer recharge, because in the past I've spent a lot of emphasis on natural recharge in response to land use and climate drivers. But now just try to talk briefly about managed recharge. And so a lot of interest in the Colorado River Basin, and this is the Arizona region. And so this is the Colorado on the left. And you can see the Central Arizona project then that brings water from the Colorado into these active management areas, Phoenix, Pinal, and Tucson active management areas. And so they recharge the groundwater using these spreading basins. And so they continue to pump groundwater and recharge it then through spreading basins or switching from groundwater to surface water irrigation. So it's a lot less expensive for Central Arizona to pump groundwater rather than treat the Colorado, develop a treatment plant for the Colorado River water to use that directly in municipalities. So it's about 1,000 times less expensive to continue pumping groundwater and recharging it through these spreading basins. And they also use inefficient surface water irrigation, recharges the groundwater. So that's also important to consider. With managed aquifer recharge, people emphasize intentional uses, but I think sometimes unintentional. The aquifer cannot distinguish whether we're intending to recharge it or not. It just takes the water. So there are a lot of opportunities these days with the satellite data and you know, a lot of different types of modeling. And I think this is geared towards the National Water Model. But then artificial intelligence and machine learning approaches and trying to bring all of these different data and harmonize the data so we improve our understanding. And then we should not forget in situ monitoring, which is also extremely important to understand the processes that are going on. Nobody seems to read my papers these days, so I try to do podcasts. And so if you're interested, you can check these out. This was a member-led event for the Nash Academy and interviewed various people at different times and really enjoy it. Not sure anybody's listening to them either. So the next GRACE mission is supposed to launch in 2028, very similar to the previous missions. So we won't see a great increase in resolution unless the Europeans launch an independent set of satellites at the same time called the MAGIC. So I realize this is a virtual presentation, but I do miss being with people, and I really appreciated the Powell Research Group because we had NASA, USGS, and academics working together, trying to better understand all of these data sources. So just to summarize then, when we compared GRACE data with global models, we found that they underestimated water storage trends, increases and decreases, and maybe because the models had limited storage capacity. Climate is a major driver of storage trends in many aquifers in the US, either directly through recharge or indirectly through pumpage. And human intervention then can amplify or dampen these climate impacts. And we need to manage surface water and groundwater conjunctively to optimize water resources, and especially within climate extremes. So thank you very much. I'd be glad to answer any questions.
Thank you so much, Bridget. That was excellent. Appreciate your time putting that together. Are there any questions for Dr. Scanlon? I'll give everyone a few minutes a minute or two to type.
While waiting for the questions to come up, I have a question. Bridget, I read almost all of your papers. So that's one thing that's you know, get out of the way. But you know, the PNS paper on global models underestimating trends and increasing or decreasing of total storage. But the global models don't really have the biggest reservoir of water, which is groundwater, which is the dynamic groundwater storage and the recharge you talked about, and the pumping taking out you talked about. None of those are in the models, right?
Right.
We
So
expect that.
well, yeah, but I mean, even still people, the UN and all these groups are using these models. And so,
Yes.
I mean, I think it was important to point out, and I greatly appreciated the modelers collaborating with me on that effort to compare them. I mean, so I wasn't trying to say GRACE was better or worse, but I don't think that those modeling groups had really compared to each other that much. And so I think some of those were surprises, why they differed so much among each other and with the satellite data. But another nice aspect is Lenny Konikow emphasizes that when we pump groundwater, only about 15% comes from aquifer storage, and the rest, 85%, comes from capture. And when they use the PCR global water balance model at a global scale and included or excluded capture and included groundwater, they found about similar percentages. So very important to consider, like we see from Mississippi, when you pump the groundwater, you're pumping a lot of groundwater, but you're really capturing surface water, so you're not changing the storage that much. So some World Wildlife Foundation said, should we move ag from California to Mississippi? And they said there are a lot of other factors. So socioeconomic factors and migrant labor force and all sorts of things, pests and different things. But anyway, it's interesting and really trying to get people to think about the things together. Groundwater and surface water. So somebody said, will you write a review of groundwater? Well, it's connected to surface water.
Yep.
Anyway.
Yep.
So we have two questions coming from the panel. The first from Wouter. Hi, Bridget. Thanks for the great talk. When it comes to highly local recharge in the more dry areas, can you speak a little bit about if or how fast any of that recharge would move laterally in the subsurface?
Well, I mean, it would depend on the aquifer system. So in sandy aquifer, I mean, groundwater flow rates are very low relative to surface water flow rates. And so in a sandy aquifer, it would depend on the conductivity. But I mean, in a karst aquifer, like the Edwards aquifer, things like that, it would move very fast. you know, you've been in caves probably and you've seen, it's just like an underground surface water system. And then in a low permeability, well, most aquifers are in low permeability, but a moderate permeability would move maybe meter a year or slower than that. So it does. So sometimes people thought, well, you know, the northern high plains is connected to the central and southern high plains by lateral groundwater flow. But actually the flow goes from east to west, and it's so slow, you know, we don't see it. There's no connection, you know.
Yeah, yeah. Next question is from Martin. He says, hi, Bridget, you showed results from a range of spatial scales, from the point scale to the GRACE footprint. Can you talk about some of the spatial scaling challenges?
Well, I mean, I think sometimes it's important to get down to small scales to understand processes, but then you can upscale and they can apply to larger areas. So, for example, when we started doing the playa studies, you know, I mean, after the fact, you always think you knew that, you know, they really did think that the playas were evaporation ponds. I mean, that's why municipalities discharge waste in the Department of Energy. And so because they had thick clay soils underneath them. And they but until you did those, looked at the data, the pressure data and the chloride data, you know, we didn't know that they were recharge features. So, but then you can apply that over the entire Southern High Plains and understand that the playas are recharge features. So sometimes you need to get down to small scales to understand processes better, but then you can apply them to larger scales. So we need all scales, we need all tools, we need everything, you know. I mean, as I mentioned earlier, you know, a lot of hydrologists are allergic to GRACE and, you know, but I think, you know, total water storage or terrestrial total water storage is very important because it gets the net effect, you know, on pumping and recharge, you know, so it's kind of like your bank balance. So it's important to be open and to all sorts of things.
Definitely. Thank you. And then the next part of this question was, one of the interesting parts of your presentation were the roles of humans in shaping the terrestrial component of the hydrologic cycle. This came up in other presentations also. To what extent do you think it is necessary to include humans as an endogenous component of the system? Or is it sufficient to include human-induced change as an external forcing? How do these answers depend on the time scale of the hydrologic prediction from days, seasons to decades?
Well, I think at the decadal timescales, I think it would be important to include the impacts of humans. And I mean, we've seen agricultural impacts globally, southwestern US, Australia, dryland salinity problems, West Africa, you know, water tables rising, ponds appearing, you know, it really changes the whole landscape. And so very important. So, I mean, one aspect, you know, a lot of people in the past, maybe 15 years ago, I can remember saying to somebody, land use change is very important to consider. And he said, well, land use is just part of climate change. You know, that's when everything was climate change. And, you know, so it's really, and who's changing the land, but oftentimes is the humans. And could we do it better? I mean, you know, when we heard this morning about the Midwest and the corn and the policies, you know, so you walk down to your plane and you see, you know, the airline saying we're going to have sustainable fuels, and silo just thinking about the fuel energy issues, but then they're going to maybe nuke the groundwater, you know, or whatever. So I think it's important to think about the trade-offs, and I think very important to consider human impacts. And we've heard from the earlier presentations how important, you know, the tile drainage, all of these things, very important to incorporate them into the modeling analysis.
Absolutely. Absolutely. Any other questions from the audience?
I think maybe I put everybody to sleep.
We have another one from Wouter. He said, it's my understanding that there's a fairly wide range of climatic conditions over the High Plains region. Do you see that as a main driver of hydrologic behavior here, or are there dominant components mainly related to groundwater and human impacts?
Well, I think you need to consider both, Wouter. I mean, climate is important, especially in the northern high plains, you know, where you're recharging through the sand hills, and but also irrigation is a huge driver. In the central and southern high plains, when that, from a groundwater perspective, climate may not be that important, but it does affect pumpage. So that indirect impact is very important, because early studies I remember reviewing, and somebody said, you know, ENSO is very strong correlation with the recharge or water levels or something. So there's huge recharge during El Nino. And I was thinking, how does it zip through that thick unsaturated zone? But thank goodness people realize it's the pumpage that's changing. So all of these things need to be considered. You know, the ply is just 1% of the land surface, but they change, and that could change flooding, you know, their extent and during wet years and stuff. So I think you need to consider all of the above and understand the linkages and the feedbacks among them.
Makes sense. We do have a question from, let's see, yeah, from the audience here. How effective is GRACE TWS data in depicting the distinct and combined influences of ENSO and PDO on terrestrial water storage patterns across different regions? What are the constraints to be aware of, if any? And this is from Gutta. I can't see the full name there. Gutta.
Well, as I mentioned earlier, we need to look at everything. I mean, you know, when I started my career, we had very little data, you know, so we had to collect it ourselves. Now we have so much satellite data, but more is expected of the younger generation, you know, because you have more data available, you have more data analytics tools and all of these things. So you're not really going to get ahead of the game because more is expected of you. So I think GRACE is very valuable in showing impacts of climate teleconnections on water storage, as long as you consider pumpage, you know, that you consider all of the parts of the water balance when you're evaluating the data. So one thing is to just look at the straight relationship between climate and GRACE, but then you have to bring in, you know, what else is going on? What is the context? I mean, it was an earlier study on the Colorado River Basin, and they attributed most of the gray storage depletion to groundwater pumpage. But actually in the upper Colorado Basin, they're not pumping any groundwater. It's all surface water irrigation. So you can't just look at one thing. You need to look at the whole picture. And we have looked at GRACE impacts on climate teleconnections in sub-Saharan Africa, and you know, I mean, it's very valuable in looking at these things. But you've also got to look at a lot of other data. And if you've got a lot of ground-based data and modeling data and other things, you need to consider all of the above.
Thank you. Any other questions? That was our last question in the chat and Q&A moment. Maybe give folks another few seconds to finish typing, if anyone's typing anything.
So Bridget, if you are to give advice to the modeling community, what are the number one and number two things that they should consider they're not considering right now?
Well, I think that connection between surface water and groundwater, I think that's probably, and even in a Zoom call yesterday, somebody said, oh, the dynamics of groundwater is so slow, or forget about it, you know. And you know, it's the bank, you know, it plays an essential role. And so I think that's one thing. And then consider land use change along with climate, you know, to consider, those would be two things that I would put forward.
And the land use change involves water management.
Right.
Where it's too wet, too flat, and we have too much water, and there's a drainage limited environment. And in the western part, it's precipitation limited. We don't have enough rain, so we have to tap fossil groundwater. And I think by considering land use change, land cover change, hydrologically, they have profound impacts on the water balance.
And I think even Steve Lohide was mentioning this morning, even a small change in groundwater use for small-scale irrigation, like irrigation was not that extensive, had a huge impact on base flow to the streams, and so drying up streams. So very important. And we had these perceptions that, you know, oh, humid area, you know, like Steve was showing many things in the Midwest that we wouldn't even think about. We thought it would be too wet, you know, that we wouldn't see that sort of thing. So I think those connections are very important, and the impact of groundwater pumpage on base flow to streams and streams recharging groundwater, and all of that connectivity is very important to capture. So
yes.
So thanks very much for the opportunity. I really enjoyed going back looking at the old material and reviewing it, and brought back some good memories. And I hope it provided some insights, and be glad to answer any questions in the future.
Absolutely. Thank you, Bridget. So, Julia, where are we on the agenda?
We are wrapping up right on time.
Okay.
So
Yeah, right on
everybody.
time. To the minute. Oh my goodness. 12:42, we're wrapping up. So wonderful. So we should just thank the three keynote speakers this morning. They're just so insightful. I learned so much. We see the big picture. We also see the local, nuts and bolts. And these are just wonderful starting place for us to move into the afternoon session. And we will, Julia probably can tell us, there's the link to register for the afternoon session. We hope to see most of you. Thank you again. And Bridget, Kevin, and I know Steve will join us in the afternoon. We will see you again at the 2 o'clock.
Yep, thank you all. Before you all go, one announcement. The last webinar in this series will begin at 2 p.m. next week on Tuesday, Eastern time, rather than in the morning. We're trying to be inclusive of our colleagues out in Hawaii and in different time zones. So it's the same connection information that you've used to join every other webinar in this series, but it will be starting much later at 2 p.m. Eastern time. Thank you all.
Can the panel stay on?
Yeah, this afternoon. Ying, I'll send another link for us to use
For the panel. Okay.
All right.
Thank you.
Thank you, everyone.
Thank you, everybody.
See you later, very soon.